All right, hello everyone, Professor Dustin here. This video is going to be an introduction to Ampere's law. So just real quickly, Ampere's law is the cousin of Gauss's law. So remember, Gauss's law is that the flux through a closed area is equal to the charge enclosed by that area divided by this constant. The picture there being where the surface is the A there and the Q is inside of it, and you can just figure out the flux by adding up all the charge inside. And of course, the reason we like this was actually a technique to find the electric field, given that there was enough symmetry around the problem. So we want to do something similar, but we do have a problem with the magnetic field, and it's pretty easy to explain. The electric field starts from charges. Charges are sinks and sources for the electric field. In this case, I've drawn what appears to be a positive charge because it's making electric field lines, and those field lines are passing through the surface. The problem with the magnetic field is that there are no positive and negative charges for the magnetic field. There's only magnets. So every magnet and every magnetic field has a north and a south pole. The magnetic field lines kind of start at the North Pole, but they always go to the South Pole. They never stop except they hit the South Pole. So they always go like this, and you can never have a North or a South Pole all by itself. You can't break a magnet, you get a pair of North and South poles. That means that if you ever make a surface like this, like let's say I made a surface right here, that surface is always going to have the magnetic flux 0 because all the fields that enter it also leave it. You cannot have a single magnetic charge inside of the field. That's called a magnetic monopole, and there's actually really interesting theory in mathematics around things called magnetic monopoles because we don't believe they exist. Some people think they do exist. There's this whole interesting debate in physics about it, but in classical electrodynamics, which is what we are studying, there are no magnetic monopoles, so this can't happen. So we need to construct something different to get a sense of what the magnetic flux is, and then we'll be able to construct something like Gauss's law that's going to be called Ampere's law. So first, let's start with a current that's creating a magnetic field. The magnetic field we know we can find from the right-hand rule is twisting like this as the current changes. So we need to construct some kind of object which will allow us to sort of evaluate the magnetic field and also figure out how much current is like inside some kind of surface. Well, it turns out the way that since there's no magnetic flux through closed surfaces, what you do is you actually go down by a dimension and you talk about closed paths instead of closed surfaces. So just to I'll just throw out the example, which is that I create a path around that somehow encloses this this current. So like I start here and then I make some kind of path like this that's going to be closed. So I have to go back and get to the same place that I started. So there's a nice closed path. But now we have the sense that this current is encircled by the path because the current crosses through the surface that I'm like shading in now. So the path is now around the current, and the surface the current is like puncturing, right? And we usually like indicate the puncture points in some way, like right there is where the current is puncturing the surface. And so that's how we develop our Ampere's law, is by thinking about the current enclosed by paths. So right away, the sort of one-hand side of Ampere's law is going to be I enclosed, the current enclosed by something. There's going to be a mu naught here. That's equivalent to the constant that you see in the Gauss's law, but of course mu naught is the magnetic constant, so that we're going to use that here. And now on this side, we want something which is going to be the magnetic flux. As I said, the magnetic flux cannot be around an enclosed surface like that because it will definitely be 0. But what you can do is you can calculate the magnetic field around the path here. So you go around the path and add up the magnetic field all the way along the path in a dot product sense, meaning that as the magnetic field sort of emanates, so we know that the magnetic field sort of circulates around this current, that means the magnetic field hits the path in a whole bunch of places. So we want to add up the magnetic field at everywhere that it hits, and the way that you do that is you integrate. That closed circle means that the path is closed. B dotted with dl. Now that dl is a little length element around the closed path like that. It's a vector, the magnetic field is a vector, so what you're actually doing, this dot product here is taking the component of the magnetic field that is in the direction around the loop. That's what dot products do, is they grab just the part of the vector which is in the same direction as the other vector. So it's grabbing the part of the magnetic field that is along the loop. So if it's coming like directly into or out of the board, this DL will pick up nothing. But in this case, the current is doing this wavy thing, so it's going to pick up the magnetic field every time it's parallel to a part of the little path vector. So that's the basic setup for this problem. Now let's do what we did for the Gauss's law and just do a couple simple, real easy examples. So I'll do that over here. So let's just get like, okay, we've got one current going this way, call it I1, another current going over. And of course, currents really should be infinite. So I'm gonna like only talk about the current in like this little place in the, on the board. But of course, the currents should be going like from infinity to negative infinity, unless we know, of course, like there's a battery somewhere stopping them and starting them again, whatever, right? But we think of currents as really being these infinite objects. So you want to do something similar here for Ampere's law that you did for Gauss's law. Of course, the magnetic flux doesn't make any sense, but these guys are paths. Occasionally they're notated with little gammas like that. So I will call them gamma, but it's whatever the path is. So if I just give you a path and say, it's called the magnetic circulation, this thing. It's not the magnetic flux, because the flux is like the flux through a surface. But this is just the amount of magnetic field that is in the direction indicated by the little integral sign. So I will try to say magnetic circulation, because that's the technical word, but it's just the integral of the dot product of the magnetic field. So what is this circulation if I pick like a surface like that? Gamma, let's call that gamma 1. Well, this integral over gamma 1 is 0 because there's no charge there's no current enclosed by that loop. Now, imagine if we tried to actually calculate this thing. We have 3 sources of the magnetic field that they're circular around each wire. We're trying to calculate the magnetic field around this crazy loop. It'd be impossible, right? But it doesn't matter. No matter what we did, we would get 0 because if there's no enclosed current, there is no circulation. Okay, so do something else like this. So that one encircles I3, and I'll call that gamma 2. So gamma 2, the circulation of gamma 2 will be B dot dl. And that is going to be mu naught times I2. I3. Easy. In fact, I don't even really want to do any more examples. It's so easy, but let's do one. So let's say I had a weird shape that was like, went over here and then underneath, and then this way, like that. So enclosed I1, I2, and I3. Call that gamma 3. Circulation around gamma 3 is just mu naught times I1 plus I2 plus I3. So it really is that easy. Now, you can do sort of tricky things where you can like try to enclose more than the same current twice or some weird thing like that, then they cancel. Doesn't matter. We're not going to really deal with that kind of detail when we try to do these problems. But that's the essence of Ampere's law done the very first way, which is just using it to calculate the circulation of the magnetic field. Okay, so now that we've had a chance at doing that, let's now use Ampere's law in the same way we use Gauss's law to calculate the field that we care about. So this is going to be like Gauss's law. We need to pick situations very carefully. In general, we won't be able to do this because if you don't know what the magnetic field is, that you can't do this integral, right? You can do all this stuff that you want, but trying to figure out what the magnetic field is from a generic path is like totally impossible. So we don't try to do that. What we try to do is if we have very special situations. So this special situation we're going to do first is a current. And then we're going to try to find the current at a point P on one side of the wire. Now, we've done this in class already. We used the Biot-Savart law to do it, and it took forever, right? So the point here is that there's a way easier way of doing this using Ampere's law. So the first thing we need to check that this dot product is going to be sufficiently easy that we can just like pull enough out of this integral so that we can actually do the problem. So first what we're going to do is we're going to check the direction of B to see what the direction of B is everywhere. So remember I taught you the right-hand rule number 2, the screw rule. If you take your thumb, point it in the direction of I, and curl your fingers, that will tell you the direction of the magnetic field. So this is a straight wire, bam, it's going this way, that's the direction of the magnetic field. So right there, the direction is into the board. Okay, cool. So that's into the board. So that means, and actually it's going to be the same out here, so equidistant away from the wire, the magnetic field is going to be exactly the same. We actually know that from the Biot-Savart law. But so that means everywhere around the field, everywhere around the wire, the magnetic field is going to be the same, and it's going to be just directed. So it's a constant value, and I need to indicate some direction. And so what I'm going to write is I'm going to write theta hat. So theta hat is the unit vector that goes in the theta direction around the wire. So I'm thinking about that little polar coordinate system here where, z is going this way, r is going away from the wire, and theta is going around the wire. I could try to draw that in 3D, but it'd probably be confusing. So anyway, so we're trying to find it at a point P. Magnetic field is some constant value. It doesn't depend on theta. It might depend on the radius. It might depend on z. We can try to make those arguments, but at the moment we know that it doesn't depend on theta because the situation is circularly symmetric. If we rotated this to try to see if the B field changed, it wouldn't change because you can't tell the difference between this rotated 180 degrees and this thing by itself, right? Okay, fine. That's what's going on with the B field. Now dl. So dl just has to be a generic current element, but of course, generic length integration element. But I am just going to integrate around the Amperian loop, which does this, a distance p away. I'm going to define the distance it is away from the wire r, so it's a loop of radius r. That's called the Amperian loop in the same way that the surfaces are called Gaussian surfaces. I'm going to integrate around that. So actually, I'm going to keep a constant distance r, so this dl doesn't have any r dependence in it because the integration isn't going to be in the r direction. The integration is only going to be in the theta direction, so we need to make a theta integral here. So the theta integration element is going to be r d theta in the theta hat direction. Now, some of you might not be that familiar with this being the integration element, so let me just do a real quick aside about that. dl has to have units of length, so whatever the integration thing here has to have units of length. So d theta is not good enough. You probably thought dl is going to be d theta because we're integrating around theta. Theta has no units, so that's not sufficient to have as a integration little element. Another way to think about this is the unit, not the unit circle, but the arc length. I'm actually drawing this. So drawing it down here, this little dl is that little dl there. And I'm going to integrate this theta like that. And the radius is here. But of course, we know if we want to do dl using the definition of theta, sorry, this is a d theta because that's a little circuit element there, little angle element there, is the arc length divided by r. That's from the definition of the radiant, right? So if you rearrange this, you get dl is r times d theta. So your little length element is actually not a theta. It actually is an r times a d theta. Luckily, we're keeping r constant here, so that r is not going to be a problem in our integration, but it is there. Okay, now we get to the easy part. Once we have defined this, we just first have to take the dot product and then do the integral. So taking the dot product is just a matter of putting in our two vectors here. So b is going to be b theta hat, dotted with r d theta theta hat for our dl element. The dot product just acts on the vector, so we get theta dot theta, that's 1. Just like all other unit vectors, theta dot itself will be 1. So we are just left with b r d theta. Cool. So let me put that into the integral over here. So we are now ready to do this integral. First thing to do is to pull out all the stuff that does not depend on theta. So theta is the integration. The only place we're doing the integral, it's a one-dimensional integral over theta. But we know that the magnetic field does not depend on theta. We made a symmetry argument for that. And we know that r doesn't depend on theta either because r is the actual coordinate, the r coordinate away from the size of the Amperian surface. So we're going to pull b and r out. And now we're integrating over theta. The range over which theta is integrated is going to be 0 to 2 pi. Because we're going to go all the way around the circle. This is simply mu naught times I enclosed. The I enclosed is my I, my current I. Cool. It's looking fantastic because now we can do this integral. This integral becomes d theta integrates to just be theta. Set the limits 2 pi minus 0, and you just get 2 pi. So b times r times 2 pi equals mu naught times I. Finally, we want to find the field. We want to find b, divide by 2 pi r. And there you go. That's the magnetic field from a long straight wire. Now, if you notice, this is the exact same answer we got when we did the Biot-Savart law for this long straight wire. But remember, the Biot-Savart law took us like 45 minutes to get this answer. So Ampere's law is way faster. Now, Biot-Savart works in all possible situations, whereas Ampere's law only works in very specific situations. But you can use Ampere's law to simplify hugely things that would normally take the Biot-Savart law very long. And this is how you get it. Now, You have to be a little bit careful because like this answer looks like it doesn't depend on the direction, and indeed it doesn't. This is just the magnitude of the magnetic field, but I did make an assumption about the magnetic field, which is that it goes in the theta hat direction. So I do have the direction. I have to just look back at my original assumption. The assumption is valid. It's totally true for this situation, but we didn't lose the direction. We just only calculated the magnitude. I think that's about it here. So the important points are that we have this Ampere's law, just like Gauss's law. It's a critical equation expression in the theory of electromagnetism, but for our purposes, it's really about finding the magnetic field. So we get situations where like there's sufficient symmetry that we can pull the B out of the integral, and then we decide that we can actually use this to find it. The steps to using it are define the B field and define the integration element in such a way so that when you do the dot product of them, you can pull this thing out. And that can always happen when you have highly symmetric problems like this wire, for instance. So you take the dot product to get rid of the directions, you have something you can integrate, and then you notice the stuff you can pull out, do the integral you have left over, and just set that equal to the maximum enclosed charge. This dl over that thing is always going to be some kind of length, circumference of a circle or a path around some other kind of shape. It could be a square. It could be this, the perimeter of a square, but it's always going to be some kind of perimeter type thing in the same way that for the Gauss's law, it was always some kind of area type thing. So the other thing we got out of this was a discussion about the magnetic flux, where the magnetic flux through closed surfaces is always zero because there are no magnetic monopoles. Magnetic charges don't come in plus and minus. They come in collections of things called magnets, which have a plus side on one and then the negative side on the other. You can't divide them up or you'll get two magnets. So that's also a consequence or a feature that we see when we study Ampere's law and Gauss's law is that the magnetic flux is zero. So unlike for Gauss's law, you can't separate magnetic charges. I think that's about it. I hope this was helpful as an introduction to Ampere's law. Thanks very much, and I'll see you in class.